Welcome to Data Science for Energy System Modeling, lecture number 3, probably week number 3. And the past 2 weeks, we've talked mostly about time series, and we're still going to have a bit of that today. But most of today is going to focus on the spatial aspects of wind and solar potentials. So how do we actually how do we find out where there's land eligibility for wind and also solar project development? So we're going to approach that from a relatively high level. So we're not going to talk about evaluation of individual sites, of individual projects, but more from a kind of, say, a countrywide perspective, where we want to find out where, in principle, the largest eligible areas would be. And just to remind you quickly where we are in the course, we're in week 4, actually. So today's first slot will be this kind of lecture, where I'll introduce you to some of the considerations, some of the data sets. And then in the second session for today, I'll introduce you to yet another Python package. There's going to be our common pattern. Almost every week, there's going to be a new Python package to be learned. And that is called GeoPandas. And as the name suggests, it has to do with pandas, and it's kind of an extension of pandas to work with geographical data. And Cartopy is a kind of auxiliary package to that helps you work with different projections. And what projections are, we're going to touch on that in the lecture, and I'll introduce that for you. The other reason why I have the ISIS course open is there's 2 things. First, the assignment, the first assignment is open. You can find it here, and it's due on the 17th of November. And if you want to get a feel for how the process works, you can also submit until this Friday this mock assignment. Will not have any influence on your grade, but it gives you the chance to go through the grading process once. And as always, this quick kind of the same, I'll show the same slide at the beginning of each lecture, just as a reminder that this lecture is recorded, and act appropriately as you wish to potentially appear in the recordings and the live stream. Nothing new there. And today is also going to be, there's going to be another Mentimeter. Also post that number briefly in the chat, or I have actually already, but not sure if everyone who wanted to, or actually I think it should be sufficient. And there's going to be one first question that is not related to this lecture, but it's related to your progress in setting up the Python environment. So maybe I'll give you 10 more seconds to enter or photograph the QR code. I'm not sure, we had this problem last time, right? That it wasn't possible. Okay. It's the first question, whether you were already, whether you were able to set up the environment, and maybe, I think that's the main question, but kind of also should hint at the, is supposed to give me a feeling for whether you have started working on the assignments or the exercises, or whether there are any problems. And for those who are answering no, there's always the opportunity to ask after the lectures, or ask on the forum. Try to keep the kind of one-on-one emails to a minimum if there's something that, because often many people have the same problems, and then it's easier for me to pool that in the ISIS forum. But I think that I would say that looks quite good, although I would like this to be 100%, of course. Okay, good. But good thing is that 30 of you already entered this Mentimeter, which we're going to use later on today. And maybe if you think back on these capacity factor time series or wind production time series that we looked at last time, then one thing we didn't talk about at all is where did we get this time series from? We downloaded it from things like Renewables Ninja or this model.energy tool where we kind of optimized a very simple energy system. But we always took these time series as a given, and they were maybe given in some obscure values between 0 and 1. We established that these are capacity factors, kind of normed to the rated power of the wind turbine. But I'm not sure if I mentioned it, but all of these time series that we looked at so far are modeled time series, and they're not historical observation of an individual wind turbine. Yeah, there's maybe kind of two main ways how you can get to these wind production time series. Either you have a site, there's a wind turbine there already, or you have wind measurements paired with power production profiles already. Then of course, you can just look empirically at the data. But in many cases, especially if you are scoping new sites where you potentially want to build a wind farm, then of course you don't know exactly what the power production would be, but you maybe have years and years of meteorological data measured. And kind of one of the primary steps that you have to do to get to these time series is you have to get from the measured meteorological data to some kind of estimated power output. And one thing that helps you there, and I'm not sure if you've seen that in maybe other courses, is this so-called power curve of a wind turbine. This is something that in many cases the wind turbine manufacturers will publish for their on their project sheet. For example, they want to sell Vestas wants to sell a certain type of wind turbine, and they let kind of potential customers know, okay, this is how it will perform. And this is kind of a mapping of the wind speeds to the power output. What wind speeds are mapped here? It's always the wind speeds at the hub height. So it's not wind speeds kind of observed at 2 meters above ground, but maybe at 100 meters or 110 or 120 meters, depending on how high your wind turbine is. Kind of the central point of the three blades. And then there are basically four regions. There's one region where kind of the wind speed is not sufficient for the wind turbine to produce power. So there's any wind speed below the so-called cut-in wind speed. And from that on, the wind is sufficient to slowly ramp up the power output. That's region 2. That's kind of the ramp-up phase. And then there's a so-called rated wind speed at which kind of the power output doesn't increase anymore with higher wind speeds. So say your wind turbine maybe has a rated power of 3 megawatts, then above this rated wind speed, your wind turbine would produce at the rated power, which would be kind of 3 megawatt, just as an example. So these are kind of region 2 and 3 are the ones where the wind turbine is producing. In region 4, the wind turbine is not producing anymore. It's kind of this so-called cut-off wind speed. It's where the kind of wind speeds are too high, for example, in a storm, for the wind turbine to operate safely. And what they do, for example, they kind of turn out of the wind. That kind of rather than the blades facing the wind, which when it becomes too strong, they turn 90 degrees so that they are not that affected by the wind anymore and don't produce, because it wouldn't be safe for the wind turbine to do that anymore. There's lots of complicated technical stuff going on here in the middle, like even though the kind of energy in the wind speed increases, how do we maintain kind of constant power output? You can control, for example, also the pitch of the blades and things like that. This is not part of the course, but it's just here to give you an intuition of kind of how do we get from the meteorological data to the power output data. And let's briefly for that also revisit the production time series that we looked at last time. It's not exactly that, but kind of same format. You have here capacity factors given, and then wind speeds. And should be no surprise, it's quite correlated. When it's windy, we have high power output. But if we now take this data, and this is kind of one-on-one downloaded from Renewables Ninja. So both of these data items, they come from Renewables Ninja. And what I can do now, I can, of course, plot that on a kind of temporal axis, but I can also plot the wind speeds against the electricity output, right? I can take each row. Each row is a point. And I can put the wind speeds on the x-axis, the electricity output on the y-axis. And what I get out of that, well, it looks pretty much like this wind turbine profile, this example profile, this power curve I showed you before. We have kind of some cut-in wind speeds. Below that, we didn't observe any power output. Then we have kind of this ramp-up phase. And actually, we don't have any observations of what the cutoff wind speed is. That just may be the case that in the data set I downloaded, there was just no case where it was so stormy that the wind turbine had to shut off. And also here we can roughly see that kind of the rated speed is at around 16 meters per second. Okay, so why do we talk about this? As I said before, different wind turbine manufacturers, they have different wind turbines, they have different power curves, and that means that some of them can specialize to certain wind conditions. So what wind turbine is the best one for your location? It can also depend on the prevailing wind conditions. For example, if you have very frequently kind of low to medium wind speeds and very rarely really high wind speeds, then it can make sense to maybe choose a turbine that can operate at high power for relatively low wind speeds, so kind of low wind turbines. Or if you go offshore where you're pretty sure that the wind is kind of relatively stable and it's very rarely not present, then you maybe don't care that much about power output at low wind speeds, so that you don't care that the wind turbine can produce at 4 or 5 meters per second, because in, say, just hypothetical, 90% of the time your wind speeds is above 8 meters per second, so it doesn't make an economic sense for that. So most of these wind turbines, so two different manufacturers here, Vestas, Enercon, they look still quite similar. They may have kind of small differences in how quickly they ramp up, what the cutoff wind speeds are. But the examples I chose, they're all kind of 3 megawatt turbines, rated speed. And that maybe reflects roughly the most common type of wind turbines that are installed today in Germany, Europe. But the trend is clearly to have wind turbines that have much higher wind speeds. Even kind of newest offshore wind turbines have up to 15 megawatts rating. Yes.
For example, the Vestas models are the heights of the.
Yes. Yes.
And then the wind measured at the height of the turbine itself.
What?
Standard height.
Mm-hmm.
That would mean huge difference in wind speed if we take one wind speed like 30
yes.
above the other one.
Yes. So the question was kind of the wind turbines may have different heights, so what wind speed is taken here? And we'll get to that in a moment. But the short answer is that you don't typically have wind speed data at the target hub height, so the height of the wind turbine. You have it typically at some standard heights, so something like 10 meters or 100 meters. And then what you need to do is, and kind kind of as you go up, the wind speeds generally increase. So when you have a certain wind turbine under consideration, you typically scale, and there are some scaling laws how the wind speeds scale. We'll get to that actually in a second. Yes, so kind of offshore wind turbines, newest developments, roughly 15 megawatt rated capacity. Also onshore, the newer ones are much bigger. And it used to be a typical hub height of maybe 80 to 100 meters. That's also now increased. It's a bit small, but there's been some kind of survey, and the trend really has been, and this is also a little bit older now, but you can get to 140, 130 meters hub height nowadays. And there's clearly a trend over the last 30, 40 years to have increasing hub heights. Why? Because the wind speeds at higher hub height is higher, but at the same time, it's also maybe more expensive to build a wind turbine that is higher. And there's always this economic trade-off of, is it worth building it higher so that it can leverage higher wind speeds? And why is the wind, so short answer, why is the wind speed lower, closer to the ground than at 1,000 meters height? Well, you have some kind of braking effect from the terrain, and that is typically expressed through this term surface roughness. So it could be mountains that have very high roughness, very high braking effect of the wind speeds. There could be cropland or trees or cities that also have high braking impact on the wind speeds. And then maybe you have open, flat grassland or large bodies of water, then you don't have that much braking effect. So this is kind of illustrated here on this figure. Maybe it takes a moment, and it's actually nothing hidden. So it maybe takes a moment to get familiar with this figure. What you see here is you can see basically a surface layer at 0.0, and then increasing height on the y-axis. So something like 100 meters or 1,000 meters. And then this red line here, the kind of values for that, they are on the x-axis. So kind of the higher you go, the bigger the wind speeds are. And then at some point, with increasing height, the wind speeds don't rise anymore. So you have kind of some nonlinearity where close to the ground, you have relatively high braking effects. So that's this segment here. So as you go higher, your wind speeds increase quite quickly, and then it flattens out here. So if you go from 900 to 1,000 meters, you don't get that much increase in wind speed because you don't have this impact of the so-called surface layer anymore. And how steep this curve here is, this depends on the type of surface. And this range where the influence of the surface is considerable, this is called the surface layer, so where you really have kind of braking effects. And kind of as your question was, kind of for typical resource assessment of a wind park, you would take wind speeds at a given height, so 100 or 10 meters, and would then scale that to the hub height. For example, if your wind turbine is 110 meters high, you would scale the wind speeds from 10 meters to 110 meters. Or if you're even better, if you already have 100 meters, which is kind of in the rough range of most wind turbines, then you only have to scale from 100 to 110. So how do we do this? There's two main laws in quotation marks, that try to kind of, I think it's mostly empirical values or kind of heuristic values to scale a known wind speed at a height z we want to calculate the wind speed at a height z, and we have the wind speed at a reference height zr. Then we can, with a log law, so-called log law, that's option 1, we can relate the wind speeds. These are given in U. So the wind speed at the hub height is related to the wind speeds as at the reference height, as the relation is between the logarithm of z divided by some z0 and the log of z reference height to some z0. And what is this z0? Z0 is kind of a constant that maps certain types of terrain. And generally, the bigger the value, the bigger the braking effect is. So open sea has very low braking, so that Z0 is a very small value, and cities or forests have a much stronger braking effect. We'll play through one or two examples later, but this term Z0 is just called the roughness length or surface roughness. And it has in units, because you have some relations here between Z and ZR, the units here is in meters. There's also a kind of simpler law that doesn't take into account any of the specific roughness, but just kind of an average. And the average would be just to take kind of the relation of the wind speeds at hub height and measured height, relate to the relation of the Z to ZR, and then kind of you have some exponent there, and typically that's 1/7. Where it comes from, I can't tell you, but it works pretty well, pretty decently for kind of averaged terrain. So let's maybe put that to use. And for that, I've prepared that in Mentimeter, and let's just see how well you do it. So this is just the slide we just had. It's a bit small, but we want to apply the log law now, and we have the wind speeds given at a hub height of 90 meters. Oh, no, we want to calculate the wind speeds at a hub height of 90 meters, and we have measured 4 meters per second at 10 meters, and low cropland at the turbine location. So for the first try, I will give you some hints and map it to your variables. So your 90 meters would be the Z, the target height. The reference height would be the 10 meters, the ZR. The 4 meters per second, of course, that would be the UZR. And then low cropland, we would just look into this table and find the value of Z0 of 0.1. And I realized that may be not so suitable for the online people, but it's also a fairly simple calculation. I mean, what you would do now basically is you would take your UZ is what you want to calculate, and you take the UZR to the other side. So that's something that you know already. And then you just form the other expression. You take the logarithm, and then you would put 90 meters here, 0.1, and 10 meters over 0.1. And here you have the 4 meters per second. And I want to hide the responses. And I'll give you maybe, yeah, let's do 2 minutes or so to calculate that. Or let's see if 1 minute is sufficient.
The unit in is in 10 meters per second.
Yes. Sorry, yeah. So Mentimeter doesn't allow floating point numbers. So 40 would be 4 meters per second. If you want 5.5, you would choose 55. Sorry, I should have. Let's maybe go with another 30 seconds. Okay, so we have some values here close. Okay, so that might be my problem that I didn't set it up with floating point numbers, because I think most of people are correct, just in different ways. Because some put in the kind of roughly 6 meters per second, and some put it as 60 meters per 10 seconds. So the overall, I interpret that as correct. So I think the exact numbers, actually, it's supposed to show here. So it's 5.9. Okay, that's quite good. Okay, we can do the same quickly with the power law, but this time without my help. And the values are exactly the same, the input values at least. Again, maybe 1.5 minutes to calculate. That's not good, huh? Yes, so I think most people are roughly correct as well. So it's a bit lower than that. So I think the answer is 5.7 or so. I think you may have seen that. No, 5.5. Okay, that was not very clever of me. So correct answer is 5.5. So it's kind of, it doesn't match perfectly anymore. Well, it doesn't match between the power law and log law. And just because the power law, it doesn't take into account any factor of the terrain. You didn't have to use any value from the table to calculate that. So now I have a bit of a quick, okay, interesting. Okay, didn't play that one through. Do you see a question? No? Okay, interesting. My question was that one. If you took the wind speed or wanted to calculate the wind speed at hub height at 90 meters, whether it would be higher or lower if it was located at open sea rather than at low cropland. You don't need to do any calculation for that. Just need to look at the values for the roughness length. So before we calculated from 10 meters to 90 meters for low cropland, and we got 5.7, I think, for 5.9 meters per second as the solution. If we now calculated it with open sea, would it be higher or lower? I hope. Okay, that didn't work. I see any results. Okay, no, yeah. Okay, so that's kind of what I expected, because if you only have a minute to think about it and it's a new concept, then I think the first time I thought I also thought it would be higher. But actually it would be lower. So I try to explain that. So you remember we talked about this braking effect from kind of, we have high braking effect at low heights and almost no braking effect at high heights. So previously we had low cropland, which had a higher braking effect than the open sea. So the difference between a measured wind speed at low height, which has a high braking impact, it will be bigger if it's low cropland, because the braking effect is higher, or the difference between hub height and ground height, the difference will be bigger because the braking effect is bigger. So if I now change to a low braking land class, like open sea land, then the wind speed I have at the ground level will not be much less than at 100 meters, because there's no braking effect. Think of it, maybe it's easier to think of it from the other perspective. Take a wind speed at 100 meters, it's the same. And you want to figure out what the wind speed at 2 meters is or 10 meters is. Then it's maybe more natural to say, or natural to understand that if I have some terrain that breaks the wind speed more, the wind speed will be lower at 10 meters compared to a terrain where the wind speed braking effect is not that high. Yeah? So that means that this calculation, this estimation, or kind of being accurate about the roughness is especially important in more complicated terrains, because there you have the stronger braking effect and the stronger difference between the different land use classes. Okay. Any questions for that? No? Okay, good. Okay, I won't dwell on this too long, but in principle, we do the same that we do for the wind turbines, where it's relatively easy to explain because it's basically just wind speed and perhaps the direction that plays a role. But in principle, we do the same for the solar PV time series. We just have to work with much more angles based on the position of the panels, whether the panels can move, and factoring in the inclination angle or general angles orientation of the sun relative to the solar panel. So you get more output if your solar panel is perpendicular to the solar irradiation than if it's kind of tilted in some way along kind of different axes. And there's a couple of other factors that play a role, like the temperature, for example. If your temperature is lower, you have better efficiency of your solar panel. And you have to also factor in different types of radiation. So for solar PV panel, you're really looking on the direct solar irradiation, so irradiation that is not kind of diffuse, where there's no clear rays, but it's maybe scattered in different directions, and that has to do kind of with the activation of the solar cells that kind of where the angle of the inclination plays a role. But the general principle is the same. You just have a few more kind of dependent variable or input variables like the direct irradiance. Some bits of the diffuse irradiance play a role, but if you were to make a correlation of these different inputs, the last three columns, compared to the electricity output in per unit, then you would definitely have kind of the direct irradiance as the biggest effect, and then temperature and diffuse irradiation. So scattered irradiation play a smaller role. And if you want more information on that, you can read up, for example, on this HALT model, where kind of it's a paper from 10, 20 years ago that makes a relatively simple empirical model to estimate the PV power output from the irradiance and the temperature, where you then just have to factor in a couple of the angles. But the main challenge here lies with kind of really understanding the different angles of inclination between solar panel and the sun. Fortunately, you don't have to do that yourself, and you won't do that yourself in the course, at least not for solar. There's software that helps us do these calculations, which you'll learn about, I think, next week's time. There's several different software packages around for that. Some are dedicated to PV, some are dedicated to wind. There's also this one here that we develop here in the group, which really just made kind of a Python library to convert from kind of historical weather data on wind, solar irradiation, temperature, and precipitation to some form of energy systems data, and it doesn't stop at solar photovoltaics and wind turbines, but you can do very similar calculation on the time series for hydro, run-of-river power plants, or reservoirs, or dams. You also have kind of your heat pumps. They perform differently in different ambient weather conditions. There's also a way where you have to convert weather data like temperature into the performance of the heat pumps. And even on transmission systems, you have ambient conditions that can play a big role, the so-called dynamic line rating, where when it's very cold and windy, in principle, you can run more current through transmission lines due to the increased cooling effect. So there's several different angles from which kind of weather data enters energy systems, not just on the production side, but also on the kind of heat side and the transmission side. That's one purpose of this package. And the other purpose of this package is to calculate so-called land eligibility analysis. So land eligibility analysis, what is that? Let's go back to the first lecture. I think I showed you this example from Agora Energiewende, which did this online calculator where you could kind of shift a few levers, like the distance wind turbines have to keep to buildings, whether we allow the use of forests or not to some extent, and then depending on how we slide things, what we choose, whether we are conservative or optimistic, we get kind of a map where we're shown areas where it seems to be the case that at least none of the obvious reasons like natural protection areas, distance to buildings, type of land use, forests, and so on, speak against building a wind farm. It doesn't automatically mean that you should build a wind turbine there. There always have to be also the right wind conditions. You could have eligible area which has the worst wind speeds. Then, of course, it wouldn't be, from an economical perspective, eligible for wind turbine development. So that's land eligibility analysis kind of made for calculating potentials. And maybe from other energy-related courses, you've seen some graphic like this. When we talk about potentials, we can mean different things by it. And we can mean things like the theoretical potential, things like how much solar radiation in energy hits the Earth every year. That's something like a theoretical potential. It doesn't take into account any factors in where can you actually build wind turbines. Maybe you can't build the wind turbines at an elevation of 3,000–4,000 meters. Maybe not possible. maybe certain land types are just not technically made to build a stable foundation. Then we're down to this technical potential, and then we can narrow this down further and further. We can factor in economic constraints, like where would the wind turbine actually produce enough power to be economically viable. We can factor in ecological constraints or social and political constraints. And this is kind of the rough area where we're working on in this land eligibility analysis. We have kind of social, political constraints like distances to buildings is a social constraint. Keeping forests and natural protection areas untouched is an ecological constraint. So kind of in land eligibility analysis, we overlay different types of criteria that each exclude certain areas, and then we look at what's left, and hopefully that's somewhat a sustainable potential. Okay, but to calculate that, we need to work with data. We need to know where the natural protection areas are, where the buildings are to keep appropriate distances, where the mountains are, where there may be kind of a steep hill that excludes building a wind turbine there, or where's the the depth of the water, where is it too deep to build a fixed pole offshore wind power plant, wind turbine. So for all of these things, we need kind of some representation of the real world. And of course, we have to make some simplifications of how we store data on the real world. And there's two main classes of geospatial, so-called geospatial data. So data that has spatial information on the geography of the real world. And these are raster image data and so-called vector data. Raster data, so let's go to them step by step. Raster data is pretty much like an image. It has pixels, and each pixel represents an area of the globe. It's even stored in kind of image style file formats. You may have come across kind of TIFF format for pictures at some point. There's a GeoTIFF. The only difference is that in addition to the pixels, this file format also stores data about kind of what particular area a particular pixel represents, so that you can map it to some coordinates on the globe. Each of these, so kind of take this image, different shades of green. We maybe simplify it and break it down to values from 1 to 9, or each one represented by some color. And maybe say the 7 represents pine trees, and the 8 represents a leaf, kind of a leaf tree. So we already have some kind of classification of what this area is in some dimension. For example, type of tree. Could be a 0 if there's no tree, a 1 if it's a pine tree, and 2 if it's a leafed tree. And you can have, for every type of tree you can think of, you can have one number. And that is kind of a categorical data set, because each number maps to a category. So for example, a type of tree. Each pixel can have a resolution. So for example, 1 meter by 1 meter. In this case, we won't work with any data sets that are 1 meter by 1 meter. Far too much data to process if you think of whole countries. But we maybe work with kind of 50 meters or 100 meter data sets. Of course, you can also think about raster data in so-called continuous values, where the different values could, for example, represent a height. How high is this pixel cell on average? It could be 100 meters, 300 meters, 800 meters or so, and so on. So you can also store, you're not limited to categorical types of data, but also continuous data. And you can even, like in a picture, you can have different layers in these raster datasets. So in a picture, you maybe have a channel for red, blue, and green. In raster data, you may have a layer for the year 2015, the year 2020, and the year 2025. There's also, you can have kind of some other dimension in this raster data. What they have in common in these file formats like GeoTIFF, it's not sufficient to store just the image, because then you don't know kind of where this image is from. But you also need to store data about the coordinates and the coordinate reference system. So coordinate reference system is a complicated term for projection. And projection we'll get to in a moment, but it's basically kind of a mathematical model to represent the kind of Earth, so globe, roughly, on a 2D surface. So we project something that is a 3D object onto a 2D surface, like when we open Google Maps or something. Then we also have to think about, well, we have a screen that is 2D, but we have actually 3D data, so we have to take some accuracy losses here and there, but more on that in a moment. Vector data is kind of different in the way that it, rather than being pixels and being kind of a fixed rasters of fixed size, your vector data structures, they can represent specific geometric forms. For example, points, lines, or polygons. And you could, for example, have points for power plants. You could have lines, I think that's obvious, for transmission lines or gas pipelines or something like that. And then polygons, you could have a polygon that describes the boundaries of a building or boundaries of a natural protection areas. And there's a couple of more types of vector data. But the important point is that the vectors, they are kind of put together from points and connections between points. And they have different file formats. So you can always see, based on the file format, whether it's raster data or vector data. And typical formats for vector data would be SHP shapefiles, GeoJSON files, or GPKG files, for example, as well. It's kind of more new data set. Your polygon could also just represent the outlines of a country, the boundaries of a country. Okay, but we need to talk about the projections. So take, for example, and there are different types of projections that preserve different parts of the different characteristics of the Earth's globe. And in many cases, well, you can't have all at the same time, because we're really limiting the 3D object onto, we're projecting that onto a 2D surface. Because most things we look at are on 2D surfaces. But either we lose some accuracy on the area. So maybe if you look at Google Maps, for example, we have pretty big area distortions kind of in the kind of northern regions, and Antarctica, for example, looks much bigger than it actually is. You could say, okay, there are few people there anyway, so we don't care about it. But even kind of Norway, Sweden, northern parts, they look much bigger than they actually are. And Africa, on the other hand, looks much smaller than kind of more northern and southern parts than it actually is. So why did Google Maps choose something that has big area distortions? Because that means they could get other features right, like distances and angles. So for some tool that specializes on navigation, it's probably right to get the angles right, because you want to know whether you have to do a 90-degree turn or a 70-degree turn, or kind of a slight 20-degree left. So that's really important for navigation, and maybe the area for Google Maps isn't super important. also distances should be right, because when you say in 200 meters turn left, then that should be roughly true. So you can't have all at the same time. There are projections that 100% preserve the angles. There are projections that 100% preserve the area and then make bigger mistakes in the respective other category. Or there are also projections that try to find a compromise. They will have errors on both the angles and the area, for example, but overall they try to keep them small. And the coordinate reference systems, they are really just projections, like you know from high school, for example. I think most of you will have done some kind of projection, not related to maps maybe, but just generally in math. And it's kind of just a mathematical function to go from any point on the globe to a point on a 2D surface. And there's different approaches, so-called planar, conic, and cylindrical, which basically take some form of paper, for example, and wrap it around the globe in different ways, and then try to connect to the closest point. So like this cylindrical, it will kind of wrap the globe in a cylinder, and then kind of kind of expand it to the inner walls of the cylinder. And once you kind of roll that out, you will have kind of a projection that looks like this. And the cylindrical, they are particularly known to have area distortions in the north and the south, which is, I think, intuitive because you have here the biggest distance between the globe and the kind of inner wall of the cylinder. But in any case, some information is also always lost. You have these different types of projections. They're categorized. You may have heard of the Mercator projection, maybe the Mollweide projections. The others are maybe less known, but they all have like these categories of preserving the angles, preserving area, preserving distance, or kind of these compromise projections like the Robinson projection that tries to minimize the distortions. Yeah, so if you kind of go here through the different types of projections, so this is one cylindrical, one conic. So the conic ones, they preserve the area. There's a compromise one. If you look at the aerial distortion is quite big here, but almost no aerial distortion for the equal area projection, as the name says. And then you have the opposite here and here between the conformal and the equal area projection. And then this one here maybe has less extreme errors on either side, but still errors on both ends. So what I thought is, before we go through a range of different examples of data sets that we're going to use, let's do a quick Mentimeter session. And there's actually one that I forgot from before. So this, this is not good because you always see the answer. So it's a guessing question. How many thousands wind turbines you think they are currently installed in Germany? Maybe this is more of a fun question I thought we could do. Okay, so the correct answer is 29,000. There's 29,000 wind turbines. And you could say it's averaging maybe at 2.5 to 3 megawatts, then we're roughly at 90, or a little bit less than 90 gigawatts of wind turbines. But the actual question I wanted to ask, looking at kind of these land eligibility criteria, some of them I already mentioned, but what data do you think we need for determining land eligibility, in particular for wind turbine development? What factors should we consider? A few I mentioned, but there are many more. And maybe let's give you some time to do that. Okay, great. I'll stop the responses so that I can cross out things. Um, so, so the one in the middle, I would actually say no. The wind speeds is not really required to calculate the general eligibility of the area. It's of course a super important factor to calculate whether it would be economical to build a wind turbine there, but just to figure out whether the area would be suitable for development, no. So terrain, yes. So two factors actually on the terrain, the slope and the general height. So maybe you don't build a wind turbine on the top of Mont Blanc or the Zugspitze, but and also kind of not in the area around it because it's maybe too steep to really develop a wind park there. And you have all kinds of other difficulties with the braking effects and so on of the wind speeds. So yes. So as reference, I would say it's kind of roughly in the same category as wind speeds. Topography also the same, like terrain. Buildings and residential areas, yes, that's true. So these can be exclusion areas themselves, but also the distances to them that have to be kept can create kind of buffer areas that are excluded. Vector data is the type of data. Cost as wind speed, per se, it doesn't tell you whether the land would be eligible. Maybe something like the cost of the land could play a role, but then you're already in kind of the economic assessment of the wind turbine, of the kind of or wind turbine or wind park. And the land eligibility, first of all, is about the general suitability of the land. Different types of infrastructure play a role, yes. And I've seen a few of them, specific ones around. So things like transmission lines, roads, highways, and so on, airports, you have to keep a distance to them. Distance to buildings we have natural protection areas, the transmission lines as well. Type of buildings, yeah, that's an interesting one. It's kind of, you have to keep distances to buildings, but maybe not every type of building. Maybe if it's an agricultural building, like a shed, is fine. Yeah, seismic activity I didn't think of so far. I think it's a good point. Forest areas, electricity grid, yes, it's all good. Building distance we had, inclination. Something new. Wildlife. So yes, goes in the direction of kind of natural protection areas, but actually if you kind of want to develop a wind park, you also need to kind of see if it's a kind of bird habitat, for example. That might also be a reason for exclusion. Different types of land use are maybe not compatible with wind turbine development. But that's also sometimes, I mean, you can put a wind turbine on a field, probably. You can maybe not combine crops, so not all types of crops directly with a utility scale PV system. There are new concepts like agrivoltaics or maybe vertical solar panels between kind of different types of crops. That's also changing, but sometimes different types of land use exclude each other. And I would maybe keep it at that, and we'll go through a few more examples in the following. So what I brought is just a couple of open data sets that we are using when we do kind of these types of analyses in our European energy system models. But first, there was a question. Hmm? So height can be important. I mean, I'm not exactly sure, but kind of also because the air becomes thinner, the wind turbines have different operating characteristics, I think. And I mean, yeah. So I think height has, I think slope it would be more prevalent. There would be more areas excluded because of the slope of the terrain that rather than the height. And then once you go to offshore, kind of inverse height, like water depth, definitely plays a big role in kind of, for example, kind of off the coast of Norway, you have kind of big drops in water depth, and that means they can't build many fixed pole offshore wind turbines. So now new developments for floating wind turbines, but that's kind of new. So I mean, and also maybe yeah, comes with other challenges. Okay. So kind of one data set is the so-called Corine land cover data set. And basically divides the whole, it's published every few years. I think the last one is from 2023, actually. And it kind of is a raster data set and assigns one of 44 land use classes to each 100 by 100 meter raster cell. So here's an example of Vienna. So in here you have kind of in red and purple. In red you have some category that's called continuous urban fabric. We have maybe a very technical term for something that's called this built-up area, this city area. And then you have here this light yellow. This may be non-irrigated arable land, so some kind of farming land, and so on. So and there's maybe in kind of light purple, there's an airport here, so that's also marked as its own category. 44 different types of land use classes, could be grasslands, broadleaf forest, arable lands of fields, or continuous urban fabric. And this is, of course, useful in several ways. We could, for example, use this to exclude later on all the raster cells that are forest, because we don't want any forest to be used for wind turbine development. We could use the cells that are marked as urban area to exclude them, as well as some distance to them, and so on and so forth. And this data set is at 100 by 100 meter data set. So for countrywide studies, that's probably enough. But I can show you here one example from one master student I supervised at some point, who compared two different data sets. So this kind of so-called Louisa data set, which is taking the Corine as a basis and then tries to enhance it and enhance the resolution to a 50 by 50 meter resolution. So it's not twice the precision, but actually, because you have for every 100 by 100 meter raster, you now have 4 pixels with a 50 by 50 meter resolution. So you have 4 times higher resolution. If you take here Berlin, you have kind of quite different picture. And this might not look super relevant here, but you have maybe some more precise gaps, or you have kind of some isolated areas of, for example, a single building that is classified as built-up area that then on its own may create 100 or kind of 1,000 meter buffer around it. So generally, when you have high resolution data sets and you want to create buffers around certain categories of the land, you get more excluded area than if you have a broad or coarser resolved data set. So resolution in these data sets matters, comes with a computational cost, of course, to process them. But in few cases, you will have data that, like continental scale data, that is higher resolved than 50 meters. Well, better depends. I think higher resolution would be always better because it's more accurate and applies actual criteria like buffers around buildings more accurately, but it will lead to bigger exclusion areas just because it's more accurate. Yeah. Okay, so for the remainder, I brought the example of Austria just because it fits better with the layout of the slides as to have something that is wider than high. So that's why I didn't choose Germany, for example. What I show you here is kind of a selection of some land use classes that are settlements in industrial areas. So 2 classes where we would that we would typically just exclude. You can see here urban areas around Vienna, for example. You can see Innsbruck here, for example, and that makes up around 6% of the area. And if you look at, for example, in the same data set, the agricultural land, then that makes up the vast majority of the country's area, kind of 30% for an individual set of classes. And you can see kind of the Alps, you maybe don't have that much of that, but then kind of northeast and eastern Austria, you have much more of that. Forests look like that, 40% of the area, and then other vegetation, another class. You maybe see that more in the kind of mountainous areas like grassland, for example, makes around 10%. All of these land classes are listed here, and they are all associated with some form of code. So you have, and don't ask me about all of these vocabulary. I can't tell you what all of these mean. But for example, you have here pastures, olive groves, vineyard, rice fields, dump sites, airports, port areas. These are kind of, this is the list of the 44 land use classes that you can distinguish here. You even have beaches, natural grassland, moors, and so on, bare rocks. And kind of a subset of that you would exclude, a subset of that you would explicitly include and not exclude anything else. And we can kind of step by step build up exclusion areas from that. And in addition, we maybe take into account other data sets. So let's kind of go through a few additional data sets. So for example, here, that was kind of your question about areas with high elevation and slope. Kind of we can exclude some fraction of that. So everything in green we would typically exclude. There's a data set that's called GAPCO, Global Terrain Data. Gives you at land and sea, so you can use it both for excluding mountainous areas as well as excluding deep sea water for offshore wind. Here you have kind of an image of the different natural protection areas. One for Europe, at least, is this Natura 2000 data set, which gives you kind of, shapefiles, actually vector data for the different natural protection areas in Europe. There's also a WDPD that is kind of the equivalent for the whole globe. And you can see kind of around 18% of the land area in the EU and 14% in Austria is natural protection areas that we would typically exclude. You can see kind of the exclusion areas, they can be completely different. And in the end, we kind of want to overlay all of them. So other things that you can also, someone mentioned in this survey, kind of habitats and designated areas under Habitats and Birds Directive may also be excluded. And there are also so-called nationally designated areas, kind of lower tier protection areas for land that can also, depending on the state regulation, eligible or not eligible for wind turbine development. And then if you go back to the first category we looked at, but now inverted, so all the white bits are the kind of industrial areas, urban areas, built-up areas, buildings. And if we considered nothing else, no other criteria, no natural protection areas, the green bits would be what would be available. So I want to illustrate the effect of different buffers, different buffer criteria on this exclusion zones. So here we didn't put any buffer, a 0-meter buffer around built-up areas. And this kind of these so-called setback differences, they can change, they can be different between the different countries. Some countries are more strict, sometimes some countries are less strict. But if you take 0 meters and go to 500 meters, there's still a relatively lax criteria by comparison to, or if you look at the different countries. You're now excluding not 5%, but 20% of the area. If you go to 1,000 meters, you're not excluding 20%, but 32%. And I think that's it. I didn't go much further than that, but you would have quite considerable effect, especially, yeah, it's a bit declining, but it's still quite a substantial effect for kind of relatively moderate distances, because there are countries where your distance may be as high as 2,000 meters. Okay, so just a sample of kind of roads and airports. This is of course not all roads in Austria. Just as an example, what you would typically keep around the roads for wind turbines, maybe 200, 300 meters. And then for the airports, just because of the radio beacons, you would keep 7 to 15 kilometers around the airports that are not eligible for wind turbines. So we looked at kind of several individual criteria now, and now our job is to stack on top of each other each of the different exclusion criteria, and kind of if among all the exclusion criteria that we consider, if for one particular cell, one of these exclusion criteria applies, that shows up as white here, and green are the remaining bits where none of the criteria we looked at excluded the area. And I mean, this is all just, an example calculation, but we would maybe end up with something like 14% of the land area that in principle would be eligible. And what we then typically do, if we want to have a rough estimate, we would look at, okay, how dense can we build the wind turbine? So how many megawatts of wind turbines can we place in a square kilometer? So maybe something 2 to 10 megawatts per square kilometer. Then you end up in something that is 23 to 117 gigawatts of wind potential. Then you have eligible areas. You can look at what the wind speeds are in these areas, what wind turbines you want to build, and you can translate, you can get not only the kind of installable capacity, but also the potential power output and the time series of the different regions. So that's one way, that's the easy way. But I can also use this type of data set to run so-called wind turbine placement algorithms that would just kind of start somewhere and then apply some distance criteria for spacing between the wind turbines to, for example, to minimize wake effects and kind of allow the wind speeds to recover after it went through a wind turbine to another wind turbine with maybe kind of some spacing of 8 to 12 times the diameter downwind, and then some crosswind distance, 4 to 6 diameters, and the diameter would be just the kind of this rotor diameter here, in addition to the kind of distance criteria. So we would kind of look at the eligible areas, so everything that is kind of bluish or kind of blue-greenish here would be the eligible area, and we would maybe start from the top left and place our first wind turbine there, and then look at, okay, how many more wind turbines can we fit into this block? And then we go kind of step by step to the next cells where we can place the wind turbines. And then we could, there are actually algorithms for efficiently placing as many wind turbines as possible in a kind of scattered set of patches of eligible area. So sometimes it makes sense to maybe place the first wind turbine here, because maybe there's a more clever way to actually place 3 wind turbines in this patch rather than, while adhering to all the kind of requirements rather than 2. Offshore, it could look like this. You have basically the same criteria in addition to the water depth, which for fixed pole, maybe 50 to 60 meters is possible. Luckily, most of the North Sea is super flat. But for example, as I said before, off the coast of Norway, it's kind of deep. And there are some additional criteria that is not shown here. You'd, for example, exclude extraction sites of fossil oil and gas. You would exclude commercial shipping lanes where there's a lot of ship traffic. These might also kind of show up as kind of, and there's a lot of traffic here in the North Sea. So that also reduces the amount of wind, kind of area available for wind turbine development. Maybe also required to keep a certain distance from the shore. That are kind of additional criteria one can consider here. Yes, so I didn't talk much about solar, but in principle it's all the same. You just have different criteria, and it's yeah, and you have to distinguish a bit between kind of open field Freiflächen-PV or rooftop PV on buildings. The approaches are slightly different. Kind of rooftop PV, you would mostly kind of estimate from satellite imagery and kind of estimate what the or maybe a specific buildings data set to estimate how much PV you could place on the roofs in a certain area. But as a rough orientation, a really rough orientation, maybe 1 kilowatt per capita is a good estimate. And the kind of eligibility criteria might be different. And then at some point, you maybe have to think about kind of you're doing this calculation always separately. What area is available for PV, what area is available for wind. And then you have to think about maybe it's not possible to do both at the same time. And typically we neglect that factor actually. Okay, so that was a rundown through the different kind of data sets, different types of data sets that you can use. There's several examples that kind of are often given as vector data, for example, points of airports, points of power plants, for example, shapes of roads. There are other examples like natural protection areas, also often given as vector data, or the kind of different land use classes, often given as raster data. But that is kind of not to say that these data sets always have to, like natural protection areas always have to come in vector data. You might just as well get this data in a rasterized format. And to some extent, you can convert between the different formats. You can take any polygon and make a raster out of that, just as a specified resolution. So conversion between them is, in most cases, no problem. And I would say we take a break now. Actually, 25 minutes. I should say we meet back at 6 o'clock to do the second session. For today, we'll introduce you to GeoPandas and Cartopy. So yeah, and I hope that will be interesting as well.